Hello, this is Graham, and it's Friday the 2nd of August, and I want to talk about the transmission line for electric fields and magnetic fields and resistances, inductances and capacitances. This is the standard Telegraphers equation done by Heaviside. The only difference is I've taken the shunt resistor, which is already defined here, and we want the fourth Laplace transform. Remember that there are 12 equations in Laplace, and they're grouped into three, but there's a fourth load of three differentials and integrals that describe the memristor, which is not really used in electronics, but it's an important component because this is a model for space-time. So think of this as capacitance of the dielectric of a coaxial cable for a satellite system or for a ham radio, whatever. And we have the inductance. This is the amount of inductance that the core down the middle sees. And rather than seeing this as L and this is normal farads, what we're going to do is we're going to divide through by mu r. So we're going to get rid of mu r, which is the relative permeability, and we're just going to concentrate on mu naught, which is the property of empty free space. And the same for epsilon naught. This is for pure empty free space. We're not looking at the dielectric of a capacitor, because there are no plates and there's no dielectric. This is the residual of what we have in empty free space, and it is epsilon naught and mu naught that are entirely responsible for the propagation of photons and radio waves. We have resistance. Now, in empty free space, this is it doesn't really make any sense. What this really is the work function of the equations for atoms. And so this resistance is how much of an electric field do you require in order to break away from the gravitational pull of the atom in order to produce what they call a forward EMF. And if you want to know what the gravitational pull is, we normally have E over I times R, and we know that the voltage E divided by R is equal to I. Well, I, remember, it has two types of velocities. It has a drift current, where the electrons are physically moving along from place to place, and we also have the acceleration velocity of the electron. For example, in an X-ray machine, a cathode ray television, very high voltages are produced, and the electron is accelerated out. So this is your velocity of the electron, and there is a straightforward equations to calculate that in meters per second. And this is your resistance. Remember that Q is equal to I times time. So this Q is actually current flow multiplied by time. So for me, I like to see that as a meters per second multiplied by time gives you length. This is the one that gives you the voltage. This is the acceleration that's needed to get the electron to break away from one of the shells. Now, that's QA and QV, E over I times R, but both of those are multiplied by time. If we now look at the Telegraphers equation for here, you can come in here, download this sheet. It'll just take you through how it's formed in very basic essence. Instead of taking this value and dividing it into this value, what we're doing is we're taking the reciprocal of that one, and remember that 1 over the reciprocal of 1 over j omega epsilon naught is actually just j omega epsilon naught, and by multiplying these two you get a number multiplied by its reciprocal, which is the same as dividing. And so we're really looking for the standing wave ratio, and i.e. when r is equal to m you get 1, and when those two are equal you get 1, and the whole thing becomes really optimal. It gives you the best transfer. And of course with omega being in there, what you're looking for is time and frequency to find an optimal place, which is what impedance matching is all about. And remember, Heaviside worked all this out because he understood that impulses down a wire propagated, and so he understood that the length of the wire needed to be matched to the length of the other wire that it was being attached to. And if you didn't attach it properly, then there was thermally removed the energy, which means that the propagating wave died out. So that's why they ended up turning the electrics right up on those and burning the wires out, because they didn't understand the difference between pulses and just DC and AC, which is all about solitons for pulses. And remember, and this is what we're modelling here. We're modelling the photon as a pulse. So the resistance and the memristance, that's a resistance, okay, but this is an impedance on DC, because as you put DC into it, it changes its resistance. And then at some point when you start putting AC through it, it becomes a resistance, a bit like a capacitor. It's if you charge the capacitor up and then you put AC through it, it's going to have a slightly different capacitance or a slightly different resistance because of the Coulomb force between the plates changing. Okay, so if you are understanding the transmission line, you'll understand that if you make microwave ovens and you design waveguides for microwaves or radar, this is how photons propagate, radio waves between these two. And these are your complex impedances, and this one are really your sort of DC conditions, which don't really exist in waveguides. But in a DC circuit like a power supply where there's no AC, because you don't want ripple and you don't want noise on your power supply, then it's all about this and this. Hence, when you have transmission lines like very high voltage electricity being generated at a power station, it has to be impedance matched to all of the transformers that step down and then eventually feed to the houses. This is the equation, which is this, because when you insert the memristor, the mathematics is beautiful and it all falls out, giving you this lovely chain rule. And this whole chain rule, which when you fiddle around with bits of nothing, it all falls out and ends up becoming this. And we can talk about that another day, but basically the omega in here is replaced by n, which becomes the number of iterations. So you're literally, this is the quantum integration of this, which is the linear form. Okay, I think we've done that one. What am I doing here? How do I get out of here? Here we go. Go away. Right, so we talked about that. This is the mechanical analog. It's exactly the same. The memristor I've made into like a Christmas tree shape because it needs to be different to that memristance. This is mechanical. So remember, the dashpot is the resistor. This is your inductor. This is your capacitor, and this is your equivalent to the memristance. I've talked about this in another video somewhere, but I'll go over this entire lot again, but in more detail. So these two diagrams I've put side by side. Let's ignore the jerk functions for now. Let's just concentrate on classic current in amps per second, ohms, and voltage. And this is Ohm's law. It's very well known. But the memristance one's interesting because what we're looking for is the rate of change of magnetic density, which, as you know, if you take voltage, you multiply it by time. Remember, these are Laplace integrators. So that's the S-plane. That is not seconds. I hope that's clear, because I did put a delta T under here to say that that's that. But when you take voltage, you get it in Teslas. And basically, the memristor says that the rate of change of magnetic flux or flux density is related to charge. And remember, on this side, time is involved. On this side, it's not, because it is meters per second or amps per second, and it's the same for that. Okay, when we look at the Maxwell's equations, which I did over there, what I did was I made this one normalized, which means this is actually 1. And so if we go over to the equations, you'll notice that this QE, which is the charge of a single electron, is exactly the same as this one. So don't multiply by m0 yet, but if you take this and you multiply it by 10 to the minus 23 over lambda e, which is the reciprocal form of the fine structure constant, you will get the charge of the electron, which is identical to that one. And so that QE divided by that multiplied by that QE, which that forms QE, gives you unity. It's been normalized. Hence, multiply a QE by m0, you get this, which is the mass. And if you take this QE and multiply by m0, you also get the mass. So they are the same. Okay, m0 here is the same as this m0. I just wanted to make that clear. Okay, so this is magnetic density, or magnetic mass as it's known, and you can see that the classic capacitor links charge and voltage and current and magnetic flux density through mu naught and epsilon naught. And the interesting thing here, of course, is that remember mu naught over epsilon naught is equal to z naught squared, which is the impedance of empty free space, and that if you take the product of these, so epsilon naught times mu naught, gives you 1 over c squared. And that gets plugged into the Maxwell's equation. There's loads of videos on that. I don't think we need to talk any further on this, other than I think we're done here. I think we're done. So this paper here is the same as this paper, but what it does is it says that where amps per second multiplied by time gives you charge, which is not what a capacitor does, isn't it? You know, if you stick 10 amps into a capacitor for 10 seconds, you've effectively got 100 amps for 1 second. The same as here. If you've got a meters per second and your car's going down the road at a certain speed, and then you multiply it by time, then you just end up with how long it went. So, you know, a car traveling at 60 miles an hour and you travel for an hour, the distance traveled is 60 miles. And so that's a nice analog for this. You can have some fun, because what you can do is you can literally plug in meters per second into the SI units for the definition of all of these electrical values, and it all falls out lovely. I think we're done here. This obviously is the same equation as that one, except rather than using charge, magnetic mass, voltage and charge again, we've got length, and we've got mass, and we have the gravitational force, and we have velocity. This is very, very relativistic. So you can see in here we've got general relativity, and we've got special relativity. I think that clears that one up. And there we are, charge times magnetic flux. And again, you can see that, and you can play with that. Please come in, download these 2 papers and follow them carefully. They are the same, but one's for mechanical, one's for electronic. And if ever you've done a degree in electrical engineering or mechanical engineering, your first year will most likely be covering vector calculus and how the equations for electronics are the same for the ones for mechanics. And I guess that allows you then to choose whether you want to do electronics or mechanics for your accredited degree. I think that covers everything there. Thank you very much for listening.